Welcome everybody. Welcome once again. This is the lecture number 9 of the deep learning course. In this particular session, we are going to talk about the delta training rule and the activation function. What are the activation function? Why they are required? And we would see a problem that without the activation function, we would be having a big issue. So today we are going to see all these things. These topics are actually very essential to understand the uh, uh, neural network based structures. Okay, so let us talk about this particular thing that we were doing in the last class. That we have seen that the perceptron training rule that we have seen into the previous classes was such that if you have a database, it was like that if you have a database and you start training on the database. Our assumption was this: the first assumption that we were having, that our data was linearly separable. We were assuming that my data is linearly separable. We start with the weights that were random and try to find out that how many places there is an error on my database. So when we start, we don't know, maybe 100 data points we have an error, but when we update it, it becomes 90. When we again update it, this number becomes maybe 75. When we again update it, then surprisingly it may be possible that it can again become 85. Then we keep updating it, fluctuate between 70 and then 80 and like that, and after a sufficient amount of time the error becomes zero. Since we know that at some point the error is going to be zero, then this fluctuation is not going to affect us, because we know that whatever fluctuation is going on, let it happen. At the end, when the error becomes zero, we would stop, and the related corresponding weights we are going to utilize as a learned weight. So this is the general setting that we actually follow. That in this way we do. But what happens? The number one problem is this: that this assumption that my data is actually linearly separable is actually not valid in most of the cases, most of the real life scenarios. So in this case, since we know that we cannot make this zero, if the data is not linearly separable, how can we make the error zero? So definitely there would be some error, and we want to actually minimize that particular error. But since this particular series actually comes ups and downs, so we don't know that when we are going to be hit a local minima, whether we should stop, or we should continue to find out a better value that is going to satisfy us. This was a very important requirement for us to get the things to do a right kind of training. So how to achieve this? So we have discussed in the last class that we are going to utilize something from the gradient descent, and because gradient descent is something that actually gradually reduces something. So if every time things are reducing, then we are happy that whatever value we can reduce the error, we would reduce, and then we would stop. For that particular purpose, this function that actually we are going to use as an output. For example, if we have a perceptron and there are some inputs x1, x2, dot xn input we have, and we have weight corresponding w1, w2, wn. So you know that there is a summation term, and after that there is a thresholding part. So what we are going to do now, that we are going to tell that I am not going to do a thresholding. What does it mean? So output, let's assume that possible value of output is 0 and 1. Okay. So earlier, as I told you earlier, even if this value comes out to be 0.6, I am okay with that particular value, because of this thresholding, 0.6 becomes 1, and then I go to this particular place. But this time I am telling that I am not going to do any thresholding at this particular place. So what essentially I am going to push is this: the value, that is the summation that is going to come, that is given to me, should be actually equal to 0 or 1. So my output, the summation, earlier the summation was such that it should be only above the threshold or below the threshold. This time I am telling that no, there should be a very large separation also. In the case when we want the 0 as a classification, this value should come to 0 and this value should come to 1. As you know that, so initially maybe not, this value may not be coming, it may be 0.3 and 0.9. So I'm not happy with that. I want that value so that it becomes 0.2 and it is becomes 0.95. So I want to push the parameter in such a way so that the output is more near to 0 and 1. So this is the condition that actually I am going to impose. In this new kind of scenario, if I want to find out that how much error my system is going to have, so for that I have to find out that what is the output. This is the target output and this is the output that my system has. I want to see the what is the difference between those two, because this difference should not be there. If if at the time of 0 my system is also going to give me zeros, then the difference should be small. If at the place when I wanted 1 and my system is also going to give me 1 value very near to 1, then this difference is going to be very minimal. So if I want to find out that how much error we have, I can say that target minus output square. I can put into this particular formulation. So and since multiple data items are there, I can find out that this is going to be the summation for all the x that are there inside my database. So this is the new kind of setting, and only thing that I'm going to change is that I'm going to remove this thresholding part, and because of this removal of this thresholding part, what is going to happen that the output of my system is going to be such that it should be very near to the actual output. So you can think that it is not a big problem. It is also it is reasonable thing to accept from the system. If we need 0, value should be very near to 0. If it need to be 1, it should be very near to 1. So I'm not going to put any weird kind of condition. It is a right kind of condition that we are going to pose. So again, this error function everybody recognized. Few minutes back we had talked about this, that it is going to be summation of target minus output square. So there is one more term half, and you know that this is this is a constant, and we are going to use it just for the mathematical convenience. Ultimately, our objective is to reduce the error. So if let's assume that the minimum value comes out to be 5, so I'm okay that if it comes out to be 10 also, because if if I multiply by 2, then the value would be 2. If error is 5, then 2 multiplied by error is going to be 10. So if I, instead of minimizing error in itself, if I minimize the 2 multiplied by error, it would also be the same on the same value. Let me tell you that what I mean by this. Let's assume that we have few numbers 5, 9, 11, 6, 3, 2, 8. Let's assume these are the numbers. Where is it is at what location it is minimum? This location it is minimum. Am I right? So let's assume that these are the some variables, say z. These are the z values. But if I want to find out that, can you give me the parameter, and let's assume the parameter is the what is the location. So what is the location? First, second, third, fourth, fifth, sixth, seventh. Location is 6th. Answer is 6. The 6th location, my value is minimum. If I say no, minimize 3z. So what is the answer? Is it going to be any different than the 6? If I say that no, minimize half z, then whether the answer would be different? No, answer would be same. It would again be the 6. Okay. So if the place where this z is minimized, at the same place half of z is also going to be minimized. Why I am going to use this half? Only for some mathematical convenience that will be clear to you when we are going to do some kind of operations on that. Okay. So this is perfectly okay to put any kind of constant over there. And this part, you know that we understood that what is this particular part. Now I want to reduce this error. The ultimate objective is okay. Once again, so what I wanted to tell, that the perceptron that you have seen earlier is now changed. This is a new perceptron. This is a new perceptron where there is no thresholding part at the output. Please try to understand this part. Okay, I am going to use a new kind of circuit. Using this kind of circuit, what is the advantage I am going to build? I am going to tell you that the advantage is this, that this time you can find out the best fit line that reduces the error. Okay, so if the data is not linearly separable, plus and minus are not very much separable, then we can find out something that actually best fit the data. Okay, using this kind of mechanism, we can find out something that is best fit. They are going to be best fit on the data. All right. So we want to find out the parameter. How to find out the parameter? In the previous classes, we have also seen that if there is a function, let's assume that this is the function, and we are assuming the function is convex. If the function is not convex, then we are not going to study, because most of the time we take this particular function in the error function in such a way so that it is convex. And we have seen into previous classes in the optimization class that if the function is convex, we can devise some strategy to find out the absolute minimum using derivative. So if we are here, we find out that what is the value of derivative. So derivative, if here the derivative would be negative, here the derivative would be positive, because derivative is the tan theta. So here the derivative would be negative, here the derivative would be positive. So if the derivative is positive should means that if you go into this positive direction, the derivative would be positive. Means if you go into the positive direction, for example delta amount, then your value of this particular function is going to increase. But since you are going to you are representing this using a error thing, so error you want to reduce, not increase. Okay, if you are going into this particular direction, then if your error is increasing, means what? That you should come into this particular direction. What does it mean? That parameter should be reduced by this particular quantity, not the increase. Okay, if you see that what is the derivative, with respect to the derivative, you can find out something that you say that w is equal to w minus this del E upon del W. Let's assume that you want to update the Wi, so this quantity. But however, here again there is a problem that you know that the value of this can be very large, and if the value is very large, what may possible that if you are here, you may go to this particular point, and then from here you come here, and you keep oscillating. So therefore, we want to also control that what is the amount of what is the quantum of increase into this particular formula. So we also put another constant over there, and by this then we get the right kind of equation that can give me that how to update this particular value. Make sense? Okay. So if we want to update our weights, then now we have a formula. So let us try to solve this particular thing more, and try to get more understanding that what is this value. Okay, what is this value means? What is this E? If I want to find out that what is del E upon del Wi, what is this particular quantity? So you know that there is a summation on the data items. So you can say that for every data item there is this particular term. With respect to every data item, you are going to have this particular term. Am I right? That this particular quantity you would be finding out with respect to every data item, and then you are going to find out the summation. So if you want to find out what is the del upon del Wi, so del upon del Wi would be applied on all these things one by one. Make sense? So and you know that what is this particular equation? This particular equation, what is target? There is some target. Target is a fixed value. Output is being computed using this W transpose Xi. Okay. So since we know that this summation term can be expanded in this way, and then individual terms, on each of the individual term I am going to apply the derivative. So let us apply the derivative on this particular formula. So if we apply the derivative of inside thing, so it means that derivative can go inside. And what is the derivative of this particular quantity? You are better than me. You can tell that, sir, it would be 2 multiplied by summation of d inside the d, and this is 2 multiplied by what? Td minus Od, and then del upon del Wi of what? Td minus Od. Okay, this particular quantity. Am I right? Okay. Am I correct? Okay. So if this is the formula, we can go inside, and we can understand that there is a half, and half is multiplied with all the values which are here. So this half goes away. So that's why I have put a constant over here. So we are done with this. Now let us try to understand this particular part, whatever is left. So you know that few minutes back I have told that what is the target of a particular value. Just consider a particular data item. Okay, just consider a particular data item, because this is the summation for all the terms. So if you pick any particular data item, for that the output is fixed. Okay, because in your database, if you pick any particular data item, so this value is fixed now. What should be the value of y? What is the target value? This is fixed. So it is a constant. So ultimately we are going to do a derivative of this particular constant, and then OD, derivative of the OD. So this particular quantity, and let us just focus on this particular part only. And this is actually del upon del Wi of Td minus del upon del Wi of OD. This quantity makes sense? Okay, so let me just clear some portion of the board and try to write over here. So you by yourself can tell me, sir, this quantity is going to be 0 because we have just talked about that TD is constant, so this is 0. What about this OD? You know that output is computed by this particular formula where Wi means W0 x0 plus W1 x1 plus W2 x2 dot 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 plus Wi xi plus dot dot dot. All the terms are there. So if you do a differentiation on something that has so many terms, what is going to happen? So you know that let's assume that I am going to find out the derivative with respect to Wi. So with respect to del upon del Wi, so it is a partial derivative. I am not considering other things. Only for one variable I am going to see that what is going to happen. So only all these things actually becomes a constant, except this particular term, because here only I get the Wi. Okay, all other things become constant. And when I do a differentiation over there, what do I get? Xi. So this answer of this particular quantity, you can say that this complete quantity is going to be what? Xi. Everybody is okay with me? Okay, are you happy? Any questions? Please let me know. If you have any confusion, please let me know. I think you are better than me. I always accept this. So let me substitute this part over here. So what would be here? The summation of for all the data items which are there into D, TD minus OD multiplied by what? Xi. No, not the Xi, because minus sign was here. So I can say that minus of Xi. This is what it is. So the formula for error is this that we have just achieved. Okay, please remember this particular formula. So this we have few minutes back seen that what is this particular value. Since multiple weights are there, for with respect to every weight, I am going to find out that what is the partial derivative of this error quantity, and then I can update if I have a weight I. If I want to find out what is the right value of a particular weight, then I can apply weight minus eta time del E upon del Wi. Any questions on that? Hope everybody understands this. Okay, you can write yes. Okay, you can write yes if you understand this. Okay, and also nobody is writing yes. Okay, so few minutes back we have seen this particular part also, that del E upon del W I is equal to this summation thing. We have just seen this. So now our task is done. What have to do? What we have to do? We have to compute that how much error we have, find out this derivative, update the parameter. After updating the parameter, go again find out that what is the error, update the parameter, be in this particular loop. Fine, you can do it multiple time. So what would happen? The value of error. So whatever error you are going to have, let's assume that on this particular y axis I am going to plot the error. There will be some error, but when you update this thing, you are updating in such a way so that error is going to reduce. So error would reduce. Again error would reduce. Again error would reduce. Again would keep reducing. This is going to happen. So ultimately, what would happen? If the data is linearly separable, this error would become 0. Otherwise, this would go to absolute minimum and stop. So there is a very important term people talk about, that here if you see that error would be reducing with very fast speed. Gradient would be high. Here the gradient would be low. We see that there is some point called this particular point where we can say that this is the elbow point. You can stop at this particular moment with this particular error, or that depends upon your requirement. If you wish, you can go to mode also. So there is some guidance that you can stop at this particular place. So now this algorithm, I think now you are well versed with this particular algorithm. I need not to tell more about this. This particular thing is called the delta rule. Oh, please note that delta rule is applied when your things are unthresholded perceptron. When what you have unthresholded perceptron, you start with the random weights, okay, and try to find out that how much I have to update a particular weight. Okay, so definitely you initially put it 0, and then for all the data item you collect what is the quantity, target minus output xi. Okay, this quantity, because you know that this is the thing that you actually have to find out. The gradient is going to be only this value. this particular quantity, and you have to find out the summation on all the data items. So for all the data item, you are going to find out this particular quantity, and by this you are going to see that how much I have to change. This much change you are going to add to your weight, and now you are done. So you are going to do this multiple number of time, as I showed you that your error is going to reduce, and then you can safely find out a place where to stop at the best suitable thing. Okay.
So the termination condition would be just a set value that the error should have. Like we set it initially before running the algorithm, or
Very difficult to tell at this particular point, as I told you that you have to do some kind of juggling to understand. First, you have to plot this error graph, okay, and then you understand that what is the behavior of your function. Then you understand that at how many, after how many, let's assume that here number of epochs. So technically we say that it is an epoch, but what does it mean? It means that every round, how many round we have done. So you have to understand that at how many round my error is going to reduce after this particular quantity. So you may bet on the error that if the error is less than this particular quantity, I will start. So some initial experiment is needed, and then you will start. Okay? Because you don't know that whether the error will be zero at the end or not. Have I answered your question?
yes, sir. Understood.
Okay. So there are also approaches that can directly do this, and such as linear programming based approaches can also be applied into this particular scenario. We have applied the gradient descent, and let me tell you, in all the cases when you are going to apply a gradient descent, sometimes you find out something using linear programming also. Okay, but what happens that linear programming actually requires the metric multiplications, and most of the time when your database is very large, you cannot do a direct matrix multiplication, because let's assume that you have three variables, okay, and how many with the three variables, how many equation you need? At least three equations. If two equations are given, then there are infinite many solution. If there are three equations, then you will be able to find out a unique solution out of that, provided they are not really dependent. So but most of the time the data points are too much. If there are 100 weights and the data points would be 1000, so what happens that it is over constant system. So finding out the parameter using linear programming is directly not possible. Then you go and you apply some kind of pseudo inverse kind of mechanism over there, and then you do a matrix multiplication and find out the solution. But again, you know that matrix multiplication is a very difficult task. Let me tell you, matrix multiplication is a very difficult task, because with the of n cross n size, it takes order of n cube time. And let's assume that the number of data items are only 10 to the power 5, then how much time it is going to take? Order of 10 to the power 15, and you know that this becomes insane. So to find out this very number of multiplication and the thing. So that's why most of the time we actually abandon this idea of going to the linear programming, and we go to the gradient descent, because at least it is going to give us the solution. So this was the idea. So till now, where we are, and I am going to tell you a very important thing. Please concentrate on this. Number one, we wanted to find out a linear decision boundary. For that, we developed a perceptron. Okay, but perceptron can solve only our problem only if the data is linearly separable. Most of the data is not linearly separable. Then what we said, then we have actually done a very unique kind of development, that we said that we are going to use the delta rule, and we are going to remove the thresholding part of that particular neuron, and we are going to remove the thresholding part, and after that what is going to happen, that I am able to train this thing to the best fit, to the minimum error hypothesis. So we are very happy. So earlier we had a problem that we were not able to train for the real databases which are not linearly separable, but now we have solved a particular problem. Make sense? We are happy. Everybody should feel this happiness, that earlier we were not able to solve the real data problem. Now we are able to solve this real data problem where the data is not linearly separable. Who is not happy? Sir, nobody is happy. So who is happy? Okay, very good. You should be happy. Sorry, I can see only one happy student. What is happening here? Yes, many students will be happy. First, you try to understand what is the importance of this particular result. Otherwise, when I am going to tell anything else, then you will not be able to go ahead with the development that I am going to have. Okay. Okay. So we are very happy because we have solved a problem that real data are actually not linearly separable, and for them we cannot use the perceptron to find out linear decision boundary. Now we have something like this. So, okay, but again, my problem is not that simple. Also, sometimes, as I told you, that my data could be like this, where negative items are here, positive items are here, and maybe some positive items are here also. First positive items are here also. So, into the previous sessions, we have seen that a single perceptron was not able to do a very good job if this kind of data arises. And again, this is the real life scenario that most of the time the data is not directly linearly separable. Then again we have a problem. Understand? So again we are into the big problem that okay, this kind of data would come. What we would do? So no problem. Into the similar way that we have seen earlier, that we can draw multiple lines, and using multiple line we can develop a logic. Everybody understand? If this is the data, what we have done in the last class, that we have, instead of using a single neuron perceptron, we have used a layer of the multiple layers of the perceptrons. What do I mean? That first layer I am going to put 3-4 lines. They are going to represent 3-4 lines. At the higher level I am going to combine them. At the higher level again I am going to combine them, and I am going to provide the input and see what is the output and do the trading. I am done. Okay. Are you ready? Do you understand what I told? If the data is of this particular type, then we should develop a neural network. Yes or no? No problem? Yes or no? Yes. So then we should develop this kind of thing. Okay. But and here, what are the perceptron? These perceptron are special perceptron for which we have removed the activation thing. Okay. Let us try to understand that what would happen that when we are going to create a neural network using unthresholded perceptron. So when we have a unthresholded perceptron, okay, or which is my latest invention in our class. This is our latest invention. That this is a good thing to be used as compared to the original one. So this is a simple circuit, and I know that you would not appreciate my drawing, but let us kindly bear with me. So let's assume the x is input. Okay, x is, there is some data point has been input. X, it has only two attributes, x1 and x2. So into the first hidden layer, this is the hidden layer where two unthresholded perceptrons are there, and at the output layer there is again a unthresholded perceptron. So if I ask you that what is the output at this particular place, can you tell me? So let me tell you what it is. So x is here. So what is the weight? Let's assume the weight is three values I need over here. Not three values I need over here. So this is the first one. So let me call it first one. It is the second one, and it is the third one. Okay. For the first one, weight is W10, W11, W12, W20, W21, W22. Any problem in that? Here the weight are W30, W31 and W32. Any problem with that? So whatever input here it is multiplied by W30. Whatever output here it is, what is the output here? If I input the x1 at this particular place, x1 will be multiplied by W1. One is multiplied by 10, and x2 is multiplied by this. I can say that this particular quantity is multiplied by weights. Once again, let me tell what is happening. So what I wanted to tell, if I say that this is the weight 1, this is the weight 2, so what is the output of this particular neuron? Perceptron. What is the output of this particular perceptron? Once again, 1 minute. What is the output of this particular perceptron? And we know that W transpose X, this is the X. So output is W1 transpose X, because this is the W1. What is the output here? W2 transpose X. So what is output here? Again, the input is these two values. So I can find out that this value is multiplied by this. I can say that W30 into W30 into 1 into 1 plus W1 transpose X is multiplied by W3 1 plus W2 transpose X is multiplied by what? W3 2. So this will be the output. How many of you agree with me? Yes or no? Can you write yes? Okay. So this is the output that I have. Output is equal to 30 multiplied by 1, and this weight multiplied by this quantity, this weight multiplied by this quantity. And we know that what is this value. Okay, this value is not very alien to us. We know that this value is 1 multiplied by W01 and x1 multiplied by W11, x2 multiplied by W12. So let me at this particular place put this particular exact equation. At this particular place, let me put the exact equation. Here also, let me put the exact equation. Okay. Let me further simplify it. So all of you are better than me. I know into the mathematics. So you can tell me that, sir, this is the W30, this is the W10, this is the W20. They are multiplied by with some weight. So these are the values. I can find out another value because this is W30 plus 31 into W10 plus 32 into W20. So it becomes a one value. Similarly, with respect to the x1, if you see the with respect to the x1 is here and here. So what is the multiplying factor? So multiplying factor is this multiplied by this multiplied by this. You can see that here is a something and there is a x1. And simply you can find out there is some other value multiplied by this. So who cares about the actual values of weights? Okay, because ultimately we are just wanted to understand that there are some weight and it is going to be going to be multiplied with the input and we are going to get the output. Okay, what do I mean by this? Very important line, that there is some value, then there is some another value that is multiplied with the x1, another value that is multiplied with the x2. Okay, means if this is a kind of a structure, do you give you any idea that what this kind of a structure is? Okay. So it is an expression of a single perceptron. This is the expression of a single perceptron. Means if I have a single perceptron in such a way, so that there is this particular weight where W0 is actually here, W1 is equal to here, and W2 is equal to here. So this is the single perceptron. Ultimately, our objective is to find out the parameter. So whatever parameter, let me say everything as a fresh. I had a problem. For that, I have devised this kind of neural network. And let's assume that I have discovered the parameter. Okay, let's assume that Ayush was thinking that I am going to make the neural network, this kind of neural network for my problem. But Ruchir came with this kind of circuit. He had made this circuit, and Ayush had trained this circuit and got the output, the same output which you would get by having this circuit. Are you able to understand this? Because mathematically they are same. How many of you can appreciate this? Is it an issue? Do you understand? Understood? So both two students are going to have the different approaches, but they are going to get the same result because ultimately he would also find out some W's, and those values correspond to the sum value of the Ayush. There is a direct relationship between these parameters. You can see that there is a direct relationship. So both the circuits are going to give you the same output. What does it mean? Whatever big circuit Ayush come up with a neural network kind of big circuit, this is going to be the Ruchir one because he is going to use a single thing. So we were solving a big problem, and to solve that problem, we have reduced the thresholding part. But if you remove that particular thresholding part, we are dead, because whatever big circuit you can come up, this actually collapses to only single perceptron. So while we have solved a very important problem, of convergence, but actually we are stuck to the generalizability. Now everything is actually single perceptron. So this is a big problem. Okay. Okay. So what should be the solution? Okay. Again, we have solved a problem. Now we are stuck. What should we do? So next thing is this: why we have reduced this particular thresholding? Because it was having 0 and 1. This was not gradual. This was the problem, that it was not gradual. So can we do something to find out the gradual thing? The answer is yes. You can use a activation function. Activation function is nothing more than this, that a function that have a continuous value. Okay, instead of 0 and 1, if we have a continuous value, then we can utilize this particular function as an at an output. For example, in this particular circuit, as I told you, that after finding out the summation over here, you are going to apply a activation function. Activation function, few example of the activation function are sigmoid, tan H, soft plus, and ReLU. We are going to discuss about them in a short while. So few activation functions are this. Once again, why I am going to utilize this function? Because if I don't use them, then whatever big network circuit you are going to come, they collapses to the single value. Okay, if I put a non-linear activation over here, okay, just seen with this particular formulation. Okay, if I put a non-linear activation at this particular location, okay, so this W transpose becomes something. W transpose at some non-linearity has been introduced. Then can I reduce again this into this particular formula? No. This formula, this reduction, this linear combination, they actually goes away. So this term would remain into your equation, and therefore now the circuit is not going to collapse. All right. So I am going to see an activation function over here, and as we have discussed, this activation function should be what? Should be smooth, because they should provide the smooth value for all the values of into their range. When I supply any value, they should provide something into the range. So sigmoid function is defined using this particular formula: 1 upon 1 plus e to the power minus x. If you have a value x, sigmoid is 1 upon 1 plus e to the power minus x. This gives you the value between 0 and 1. And if something can give you the value into 0 and 1, then we can utilize this for a very important understanding, that what is the probability of the item being 1. Okay? Direct interpretation, that whatever output that I am going to get, what is the probability that it is of the kind 1. Sometimes we need the output into the -1 to +1 range, because this is two classes are -1 and +1. In that particular case, we can use another function that is called the tan h, e to the power x minus e to the power minus x upon e to the power x plus e to the power minus x. Another function. So we can utilize the tan h into this particular position. For both of these activation function, there is a small issue is this, that however they are suitable and they are good, but the only issue that comes is this, that you see that when the value is of input x is high, then the gradient becomes very small. Okay, gradient becomes very small at the extreme points. What happens that if you are into this particular area, your learning is very small, very less. Okay, here, because ultimately you are going to use the derivatives to update the parameters. So if you are into this particular place, then you are updating your parameters with a very less, and therefore, because ultimately you want this value to be -1 and here +1 and here -1, here you want 1 and here you want 0, but the gradient is very less, so you will be progressing with a very small quantum, so it will be very difficult to train. So this is the only problem. To solve this thing, we have another function that is called the soft plus. Formula is very simple. There is log, and inside there is 1 plus e to the power x. You know that e to the power x and log x are enemy of each other, so they kill each other, and ultimately you get the value of x. So because we are going to have 1 over here, so the order condition such as when the value becomes 0 and we are going to take the log of 0 is actually taken care of. So this function is you can think, what is this function? It is a kind of linear function, okay? But at the places when it is very small, then it has some non-linear kind of characteristic. Otherwise, roughly it would be linear kind of function. So this kind of function it is, okay, this kind of function. So you can see that when the value, this value is there, then the gradient is high. So learning would be fast. So when you are learning, your learning is going to be very fast. So this is actually representation where can you see that what is the gradient with respect to this. You can see that here the both the items which where for the sigmoid and tan h, the gradient is very small, but here you can see the gradient is very high. So you can do a very good learning with these kind of function. Okay. So whenever we solve a problem, some problem, another problem comes. Whenever I open a door, another door comes in front of me. So now the problem with this kind of function is this, that I have solved that now my gradient is good, but the issue is again I have an issue that finding out the soft plus is not easy, because you have to find out log and e to the power x. Both are not easy things. If you want to find out the explanation of something, then you have to do a lot of computation. Log is, again, you can see that if you want to do the approximation of something log, it is an infinite series, and you sometimes you take first few items to solve that particular problem. So again, this is a big problem. Okay, so to solve this thing, another function came, that is called the ReLU function, rectilinear unit, and that's a very easy function. And if this function says that you want to see that two values, there is a fixed value 0 and x. If you want to find out what is the ReLU of that particular quantity, so you just see that what is the maximum of 0 and x. So again, we wanted something linear, so you got the linear, and it is very good. So one more thing that I wanted to discuss over this particular point is this, that since, as I told you, that when you want to update the weight is equal to weight eta times eta times derivative. Okay. So in this particular formula, you have to find out the derivative. How to find out the derivative of sigmoid? So sigmoid has a very nice property. For example, if for any x, if you know that what is the value of sigmoid x, then derivative is sigmoid of x into 1 minus sigmoid of x. Very easy. So finding out derivative was very easy over here. Okay. So because ultimately you have to go into this particular scenario where you have to update the parameters. So you have to find out derivative also. So finding out derivative should also be easy. And if you see this rectilinear unit, so it is a super easy, because what is the derivative? Derivative, if the value is greater than, if value is greater than 0, then the derivative is 1, because derivative of x is 1. If it is less than 0 or less than or equal to 0, the derivative is 0. Very easy. So finding out the derivative is also very straightforward with the ReLU. So that's why ReLU is more preferred into the systems. And if you apply the ReLU in your network, your training time would be very less. You would be very fast. So till now, did we solve all the problems? Okay. So we have actually come up that if you are going to build a network circuit, a neural network circuit, so at the final layer, since you want to find out the probability, you are going to apply sigmoid. Inside, you apply the rectilinear unit, so that finding out the derivative is very easy. However, again, there is a problem. What is the problem? Just see this. Below the 0, what is the derivative? There is some derivative, so you would be learning. However, the learning rate is small, but you will be learning. Here, what is going to happen? The derivative is 0. What does it mean? That you are not updating your parameter. When you are into this particular area, when you are not updating your parameter, no learning is happening. It's very bad, because when you come to this particular place, after this, you cannot learn. Again, there is a problem with the rectilinear unit, and therefore the solution comes at a leaky ReLU. Okay, the solution comes leaky ReLU. There is a solution called leaky ReLU, and this says that instead of having 0 at this particular place, you put a small number, maybe 0.01 multiplied by x. So there would also be a learning. So if I use leaky ReLU, so what would be the equation? The equation would be that it would be small like this kind of circuit would be there. So here also there would be a learning. Okay, so instead of ReLU, what we are going to use? We are going to use the leaky ReLU, this particular thing. Okay, any questions on that? So
would we face the problems that we faced for a linear activation function that you explained earlier?
no, actually, what I told you now, if you in the previous slide, I told you that when you are going to apply this activation over here, then you cannot do this kind of linear combinations kind of thing. So this is not going to happen. So the network will not collapse. Okay, that's why we have, because there is e to the power x and these kind of things are there. So definitely they are not going to become a single thing.
So no, sir, I'm talking about ReLU function
Okay.
specifically. Is it is linear after for greater than zero value? So won't it affect?
So linear was not a problem, no? The problem was thresholding. When we were doing the thresholding, then my error were actually coming up and down. This was a problem. Nothing else was a problem. Any linear combination was not a problem. The problem was that my error was coming up and down, because here I was using a thresholding function. But now the things are gradual. If the things are gradual, my error is also going to reduce gradually. Understand? Okay. Thank you. So I think we have covered this into a good detail. Now I wanted to tell you that very important thing I missed over here. Let me once again come to this slide and tell you that when I am going to use activation functions, any of these activation functions which are actually going to give me a linear relationship of the summation term, then the perceptron is called as neuron. Now it is not a perceptron; it would be called as a neuron. And from now onwards in my class, whenever I am going to represent a perceptron, it means the neuron. Neuron means what? A perceptron that has an activation function, any of these activation functions. Okay, when we are going to use this thing, then it is going to be neuron. And using neuron, you understood that now you can make a big neural networks. Make sense? Okay, so here into the neuron, what is going to happen? I am going to apply activation function, and this activation function right now it is said as what? Sigmoid. Sigmoid. The formula of the sigmoid is this. We know how to find out the weight. If I develop a big circuit, how to find out what should be the weight over here? The method is called back propagation that we are going to see into the next classes very soon. Into the next class, we are going to see. We can utilize the mechanism, as we know that gradient descent based mechanism, to find out that what is the right value of the parameter. I want to tell you a very important thing right now. Focus on this. What happens that, let's assume that I have made a neural network circuit. Okay, this is the neural network. If my item, if I am going to do the, let's assume that we are going to do a classification task. If number of classes is 5, so I will put 5 neurons at this particular place. Sorry, and every neuron is going to correspond that what is the probability that the item belongs to this particular category. Okay, into the neural network circuit, what I told right now, that you can put multiple outputs. Each of the neuron is going to represent that what is the probability that item is going to be of that particular category. So into the error formula that we have seen few minutes back, it was that you wanted to understand what is target minus output, and you take the square of that. You also have to add one more point, that for all the outputs that are there, you are going to find out the summation of this particular quantity. The general formula for the error into the neural network is going to be this, where you are going to see that for all the data items, we are going to see that on all the outputs, what is the difference between target minus output. This is the error function. I think this is also straightforward and very clear. So this is about back propagation. Don't go inside this. We would. I just wanted to tell one thing. We would come back to this once again when we derive all the formula. Then we would come back to this, and I would tell you that what does it mean. Okay. Right now you just understand this particular part. That initially you have some weight. Initialize the random weights. I think you all agree this. You all agree to this, that initially I am going to have the weights, random weights. For all the data items, what I am going to find out, that I have to update the weights. How can I update this weight? How can I update the weight? Weight, what is the change that I have to add? Something I'm going to add to that. What I have to add? What I have to add is going to be obtained by this particular formula. Okay, and this formula has this kind of a structure. I'm not going to into detail right now because we have less time. In the next class, we will see, we'll find out the derivative, how can this formula come when we have multi-layer things. So next class, we are going to see the back propagation, and I also want to tell you some conventions, but I think this is fine that if we don't cover this today, maybe tomorrow from the next class with a fresh mind we can start. Okay, so what is happening? Why it comes back? So thank you very much for the joining. I would love to have any question if you have.